Hello everyone, I am Akhilesh Kumar Srivastava from ABS Engineering College, Ghaziabad. In the series of operating system lectures, we will discuss about the process synchronization, inter-process communication. This will just be the introductory lecture for the process synchronization. In the subsequent lectures, we will discuss in detail about the solutions by which we can deal with this problem. So, the outline for today's lecture would be that we will first be discussing about the cooperating and the communicating processes. Then we will discuss about what is the need for the synchronization. Finally, we will discuss about what are the different solutions for the synchronization problems, and we will then compare the solutions by the methods which they have been acquired. Now, let us first talk about the cooperating processes and the competing processes. Let us say there is an assignment schedule for a class. Usually what happens that some of the students do solve that assignment and they share it for the others. The others do copy that assignment and submit it further. So, what has happened in this case, that the assignment was the activity which was required to be done. Some of the people have done it, the others have taken the help of the others to solve their own ones. So, they have actually were the cooperating processes. But what happens in the case when there is a quiz schedule? There is a quiz schedule, and this is not the online quiz schedule, it is an offline quiz schedule wherein there are some of the teams which are actually fighting for the competition. A question is thrown by the person who is conducting the quiz, and there is a competition among the people or among the teams that who responds first. Whosoever responds first wins. So, it means that there is a competition between the teams there. Similarly, in the case of the processes, there will be some of the processes which will be cooperating, and there will be some of the processes which will be competing with each other. For example, the two processes, let us say, or more than two processes are trying to access a printer. Now, a printer is the device on which only one of the printing can take place at one time. If multiple processes are there and they are trying to access the printer, then printer is not given to all the processes all of a sudden or simultaneously. So, there will be some ordering maintained. So, there is a competition between these processes that which process will use the printer first. So, the competing processes. And then a cooperating process is that in which a process generates something and the other process consumes that thing. For example, a message is produced by a process and the same message is consumed by the other process. So, a mechanism would be required here in this case, that whatever message has been produced by one process reaches to the consuming processes. So, the cooperating process and the competing processes are the fundamentals for understanding the synchronization. In both the cases, the synchronization is required. For example, in the cooperating process, a synchronization is required for managing the messages, that how will a person or how will a process will generate the message and how will that message reach to the consuming process. In the competing process, we need to maintain an ordering by which the execution of the shared resource can be planned. So, here in this slide we are showing that there are two processes, P1 generates some output and the second process P2 consumes that item. So, we will say that the P1 and the P2 processes are cooperating processes. If there is a printer and multiple processes are trying to access that printer, two or more than two processes are trying to access the printer, those processes will be said to be the competing processes. Now, what is the reason for the cooperation? Even if in case we are doing the cooperation, in case we have the competing processes or if we have the cooperating processes, both will be said to be the some kind of the cooperation only. Then there will be some reason because of which we are doing this. The reason for this is modularity. Modularity means there is a task, a big task or big software which is to be designed by you. Now, this big software will be divided into the parts, and these parts will be said to be the modules. The programmer has already designed the modules, and it has established a connection between these modules. It means one of the module is very well connected to the other one. So, the cooperation is required between the modules. The information sharing, for example, there is a file or there is a database. So, file can be used by many processes. There is a file, this file can be opened for reading among many processes, and the file can be opened for writing also. An example of a file being used by the multiple processes is the dynamic link libraries. A dynamic link library is used by many processes when they are running. These are called the DLLs. So, DLLs are used by many processes at the same time during the execution. Since there are many processes which are using this file, we can say that this is the information sharing, the sharing of the information of the file among various processes. Usually in the dynamic link libraries, we use the dynamic link libraries for the execution of the programs, but do not make any change. In case we are making the changes also in the file, or the simultaneously many requests has come for changing the files, for example in the database, then we will say that the writings are also allowed. So, we need to maintain a coordination between writings and reading. Usually what practice will be adopted, that the readings will be allowed to multiple processes at the same time while restricting the writings. It means that when multiple reads are being performed, the writings is stopped. Even if single read is being performed, the writings will be stopped, and when there is no readings, we will start writing, and when writings are performed, it is ensured that the readings will not be performed. So, we are maintaining the information sharing through the cooperation. It means that cooperation is required between the processes to ensure that multiple reads operations can be allowed, while writing is performed, readings are restricted, and while readings are performed, writings are restricted. So, this usually can be seen as an example in the files and the databases. Now, another thing is that we can do it for the convenience. Convenience means while execution of the program, the convenience is required. For example, if you are maintaining a software, once again the modularity concept comes. In the modularity concept, we can run the different modules in parallel also. Running the different modules in parallel actually provides us the convenience, okay, and it provides the computation speed up as well. It means if we are using a software and we are running the different modules in the parallel, then obviously will be obviously the execution time of that process will be less than that process running sequentially. So, we are doing it for modularity, means the cooperation is done for the modularity, cooperation is done for information sharing, cooperation is done for convenience, cooperation is done for computation speed up. Now, let us take an example of the cooperation. The cooperation is required in between the process 1 and process 2, and this kind of the communication is required or the cooperation is required in the sense that the process P1 will be generating some message and process P2 will be accepting that message or consuming that message. You can also say that for the execution of process P2, it is required that it consumes the message sent by the process P1. So, they are the cooperating process, fine. So, the method would be or method could be that P1 process sends its message directly to P2. In this case, if P2 fails, there will be no reason for P1 to generate the message, or in other sense, if P1 fails, then P2 will keep waiting. P2 will keep waiting forever for accepting the message. So, we should maintain some other mechanism for sharing of the message. For example, P1 process sends a message to a common place and P2 process consumes that message from this place. So, there is a common memory in which a message is submitted and the message is received from here. This can be seen as an example of the email, where email is first sent to the server and the server hence sends it to the receiver. So there is a sender and the receiver. Sender does not send the message directly to the receiver. There is some entity, for example a server or mail server in between, that actually works as the buffer, and the message is sent from that buffer to the receiver. So this is one of the example of the cooperation. Now when processes are interacting with each other, then it requires in some cases that they are actually dealing with the same common shared memory. For example, here in this case, the place where the messages were submitted by P1 process and the message from which it was from the place where this message is consumed by the process P2, they are the same. It means they are actually accessing the common memory. So if they are using the common memory, there is a conflict that which process will use the common memory first and which process will be using the common memory next. Okay. Similar is the example of using the common variable. There are two processes, let us say P1 and P2 process. P1 process is executing its code, and somewhere in between it uses a count variable, and count variable is incremented. Similarly, a P2 process is also running in parallel, and then P2 process is doing its own code or working with its own code. Meanwhile, it is accessing the count variable for decrementing. So count is incremented here and count is decremented here. The common variable is used by two processes which are running in parallel. If the common memory is used or common variable is used by the different processes, we will say that this process is these processes will interact with each other at some point of time, and this interaction is in the kind of the common memory or common variable. What we actually want here, that let us say the value of count is 5. If P1 process is running, P1 process will update the count of count variable from 5 to 6, and then if P2 process is running, this will decrement the count from 6 to 5. So final value of this count variable should be 5 here. But if we allow these two operations to take place in some different order, then there will be a conflict. We will see later that how the conflict will arise. So here we are using a common variable, and because of that only these two processes are interacting with each other in some means. Now process interaction, both the competing and cooperating process need to share a common memory for updation. Count is the shared variable in the last example that both the process need to share, and if initial value of count is 5, as we already have discussed, if P1 process runs, then P2 process runs, the final value of the count variable should be 5. Now let us take consider this as a bounded buffer problem. Bounded buffer problem means there is a buffer of the fixed size. There is a buffer of the fixed size. Now in this buffer, what is happening, that a producer is there which is producing an item and keeping it here in the buffer, and there is a consumer which consumes the item from here itself. This actually relates to the example that we have taken of the message generation by one process and consumption by the another process. We were storing the messages at the common place. So wherever we were using the common, or wherever the common place was used for accessing the messages or for storing the message, that actually is the buffer, and that buffer usually is of the fixed size. We cannot have the infinite memory. So obviously we will have to keep a fixed size buffer. So here there is a producer process that produces an item and keep it here in the buffer, and there is a consumer process that consumes the item from this buffer. So access to this buffer can be allowed to one process only at a time. In case it is allowed to two processes in parallel, this may arise the conflict. So I am dealing with the conflicts only, or I am just telling you that how will the conflict be generated, and later on the later stage we will see that how this conflict can be resolved. Now let us take the solution, let us take the two processes, producer and the consumer process, and let us see that how the count variable will come into the picture here. Now, this is the solution for the producer process. In this solution, what we are doing, we are producing an item, and after the production of the item, there is a buffer size. The buffer size is telling you that how many items can be kept in the buffer. Let us say the buffer size is n, and there is a counter which initially is at 0, meaning that there are no item in the buffer. As soon as an item arrives, we check if this counter is already at n, it means there are already n item in the buffer. So, obviously, we cannot put more item on the buffer, since the buffer is full, buffer cannot be accommodated with more elements. So, if the counter is equals to the buffer size, then we will wait. Okay. So, there is a symbol semicolon, and we are in the while loop. It means that when the buffer size is when the counter is equals to buffer size, we will keep waiting. We will keep waiting until at least one item is consumed by the consumer process. The moment one item is consumed by the consumer process, the number of elements in the buffer will reduce to n minus 1. Then we will have a space for producing an item and putting it there in the buffer. Okay. So, let us say the counter is not equal to buffer size, counter is less than buffer size. So, if the counter is less than buffer size, then what we are saying that in the buffer array, in the in index, we are going to put the item produced. So, buffer is an array, in the in index, we are going to put an item produce. For example, let us say this is the example, and in this example producer process finds that the value of the count is, let us say, n, okay, not n, let us say n minus 2, and let us say in is also at n minus 2. So, this buffer, let us say, is an array. So, this buffer will be referenced through the index. So, at in index we will be inserting the produced item. Let us say the produced item is x. So, that is what written here. In the buffer at the in index, the produced item is stored. Now, after this in variable is incremented. Since we are taking this buffer as a bounded size or a limited size, and we will keep on inserting the items here, and will be consuming an item here. So, this buffer is treated as a circular array or the circular queue. Okay. For circular queue, we need to increment this in. You can think of this in as the rear in the queue, where rear is updated by the formula rear equals to rear plus 1 mod buffer size. So, this is updated for the next values. After this, the counter will be updated by 1, because one item has been inserted in the buffer. Similarly, there is a consumer problem or consumer solution. In the consumer solution, what we are saying that if there are 0 items in the queue, or if there are 0 items in the buffer, we cannot insert more item, we cannot consume an item from there. So, this will keep waiting. Now, since this will keep waiting, the next consume item, let us say the counter is not 0, it is something more than 0. So, in that case, buffer at the out index is taken in some variable, and this item will be consumed actually. After this out, or out can be referred to as the front also, the item is taken from the front. So, this out is incremented by 1, or out is updated, and finally, the counter value is decremented by 1. Since you have consumed an item, so counter will be decremented by 1, and whatever item you have taken in the next consume, this item will be consumed. So, this is the solution to the bounded buffer problem, or you can say that this is simply the NQ and the DQ operations in the queue. So, this NQ and the DQ operation is ensuring that the buffer size should not get crossed. and if the buffer size, if the counter is telling you the 0 value, it means that there are 0 items in the queue, so you cannot consume any item from that queue. But there this actually arises the problem. For example, we have done the count plus plus and count minus minus. Okay. So, let us say there are two processes, let us say this is the P0 process, no sorry, this is the P1 process, and let us say this is the P2 process. So, what the P1 process does, the P1 process, this is the P1 process, let me write it again. So, this P1 process is updating the count, but this updation of the count will be represented in the form of 3 different statements in the assembly language. When we are doing the compilation process, during the compilation process, it is ensured that in the compilation process, it is ensured that this statement is divided into the operations which can run in one CPU cycle. So, that is why we have divided it into the 3 statements 1, 2 and 3. So, this is move count, the value of the count to R0 register, then increment this R0 register, and then the value of R0 is transferred back to the count. So, first the increment is done in the register, and then this register value is transferred into the count variable. Let us say we are allowing the preemptions to take place between 3 statements, but what has happened, we will see 3 different scenarios. The first scenario says that the statement 1 executes, then 2 executes, then 3 executes. Okay. Statement 1, 2 and 3, and then statement 1, 2, 3 runs in the P2. So, obviously there is no problem. Let us say we have started with the count value 5. So, if 1, 2, 3 runs as an increment, the count value will be 6, and after which the P2 is executing the statement 1, 2, 3 and the count value will be 5. So, that is what we were expecting. First the count value was incremented and then the count value was decremented. The final value what we are expecting is 5. If we allow the preemptions to take place, for example, the preemptions are allowed. So, let us say the statement number 1 and 2 of P1 process runs, then the value of count is given to R0, and then register value is incremented by 1. It means the register value contains 6, but count even now contains 5. Now, after this P2 reads or P2 checks the statements 1, 2 and 3. So, P2 runs move count R1, it means value of count is transferred to register R1, it means 5, and then decrement, it means this is 4, and then move the value of this count to R1 register to count. So, count contains 4 now. So, count contains 4. After this P1 executes the statement number 3, and according to this the value of R0 register is given to the count. So, this is 6. So, here what we are getting that the final value of the count is 6, which is an inconsistent value. We actually want the consistent value, we wanted 5 to happen, but since we have allowed the preemptions to take place, this value is 6. Let us take this scenario. By this the register R0 contains the value of count, which is 5, and then increments the value. So, this value is 5, and then P2 runs the 1, 2, this will decrement the value. So, R0 will be containing, sorry, R1 will be containing 4, and then this statement is storing the value of R0. So, count here will contain 5, and according to this statement, this is the P2 process statement, the value of count will be 4. So, final value of this count is 4, but what we wanted the value of count to be 5, but since preemptions are allowed in between, what we can see that the final value of count is 4 in one case and 6 in another case. This is which is the inconsistent value. So, this is the problem of the synchronization. If the preemptions are allowed, then this kind of the condition will take place, wherein we may find the inconsistent value. So, this is also called the race condition, wherein there are two processes which are trying to access to the common resource or the common variable, they are trying to update the common variable. So, whosoever wins will be updating the value. So, this is the race condition, race between the two processes, that which process will set the value of the variable. Now, the process interaction, just take a brief of this. because we already have discussed this. Process interaction is in a cooperating process is one that can affect or be affected by the other processes executing in the system. Cooperating process can either directly share a logical address space, okay, and this can be done through the threads. If we have to run different part of the code in the parallel, we can say that this can run in the run with the help of the threads. And this is also this can also be said that the cooperating processes are those which is allowed to share the files or the messages. Then this can be done through the different mechanisms, and we will see that we will see those mechanisms in the form of the solution to the synchronization problem. Now, whenever there is a conflict, we will first see that there is a part of the code written, and in this part of the code there are some section of the code where we are using or where we are incrementing or decrementing the values, or where we are updating the common variable. So, the part of code where the common variables are used is known as the critical section problem. So, in a program I can use the shared variable multiple times. So, as many times we are using the shared variables, that is called the critical section, okay, and the part of the code which is doing something else is called the non-critical section. So, a part of code where the shared memory is used, this is called the critical section. This is very essential, that where we were doing the count plus plus or count minus minus, that was the critical section, okay. Solution to the critical section problem is actually the synchronization, means we have to provide this solution to the critical section problem. Two processes cannot enter the critical section at the same time. If they will enter, the method that we have seen here was actually finding out the inconsistent value of the count. So, similar condition will arise if we will allow the multiple processes to enter the critical section at the same time, okay. So, what is the solution? The solution is that while entering the critical section, we should actually apply some condition. So, those conditions are known as the entry condition or entry section, and whenever we are exiting the critical section, means we have used the critical section, we do not require it anymore. In that case, we will say that we are in the exit section. Whatever conditions we have applied, we will just remove those conditions, okay. So, the entry section, critical section and the exit section. Whenever we are writing the solution, a critical section will be bounded with the entry condition and the exit condition. This actually is the synchronization mechanism that we will use, okay. Whenever we will be designing any solution to the critical section problem, then those solutions should satisfy the 4 conditions. Out of these 4 conditions, we will say that 2 are primary and other 2 are the secondary condition. It means that first 2 must be satisfied, but next 2 should be satisfied, okay. So, the primary is mutual exclusion. Obviously, when we are dealing with such a situation where we are going to allow only one process in the critical section, the solution should ensure the mutual exclusion. Mutual exclusion means only one process can be there in the critical section at a time, not more than one process can enter the critical section at the same time. And then the progress means what? You can take the example. The progress can be understood by the example of a class. A class of 40 days have run in parallel, or you can say that continuously the classes for 40 days have run. Now, the students have exhausted. One of the students says that no, we will not attend the class tomorrow. So, next day he reaches to the college and then he stands at the door of the class and he does not allow anyone to enter the class, okay. So, that student does not have to attend the class and he is not letting any other student to also to attend the class. So, similar is the progress condition. Let us say there is a process which wants to enter the critical section, okay, fine, but let us say he does not have to, the process does not have to enter the critical section. So, it will not allow P2, P3, P3 and all these processes to enter the critical section. It means this is the condition wherein a process does not have to execute the critical section and it is restricting the other process also to enter the critical section, fine. Then bounded wait means a process has to enter the critical section, it enters continuously, it is not allowing any other process to enter the critical section. It is the process number P1 is infinitely going to the critical section, it is not allowing any other process to enter the critical section. So, this is the bounded wait is not satisfied. So, there should be some conditions by which after some time it should be guaranteed that the other process will also get the execution to the critical section. And architectural neutrality means a solution which you have designed should not run only on the few systems, it should run on all types of the systems. It should not be platform dependent, it should not be machine dependent. Fine. So, we will discuss on the next turn the solution to the synchronization problems with the busy waiting and without busy waiting. So, this is the reference for this lecture. Thank you.